Thermal fastening is the engineering process of joining two distinct parent metals together into a single permanent structure. At the extreme end of the temperature spectrum is fusion welding. By introducing a 3600-degree electrical arc, the base metals are forced into their liquid states and physically blended together. But high heat can warp, weaken, or destroy delicate components. To bypass this, engineers utilize non-fusion processes. Instead of melts, they remain entirely solid, bonded together by a molten intermediary material. This diagram illustrates the critical thermal dividing line that governs all non-fusion joints, 450 degrees Celsius. Keep the temperature below that 450-degree threshold, and you are soldering. The resulting joint is highly conductive, but structurally semi-permanent, designed for lower strength applications. Push the temperature above 450 degrees, typically settling around 600 degrees Celsius, and you enter the realm of brazing, or hard soldering. This yields a permanent joint capable of withstanding moderate to high mechanical stress. Achieving structural integrity in a non-fusion joint requires precise engineering. Whether operating at 200 degrees or 600 degrees, success depends on balancing three strict variables: the metallurgical alloy, the chemical flux, and the thermal delivery tool. The filler material, commonly referred to as solder, is a highly tunable, non-ferrous alloy matrix. In its most common form, it is constructed primarily from two elements, tin and lead. This chart plots the thermal limits. Pure tin requires 232 degrees Celsius to melt, while pure lead demands 327. Alloying these two metals drops the working temperature of the resulting matrix well below either individual element. The baseline standard across various trades is a precise 50-50 split of tin and lead. This ratio is optimized for joining large, flat surfaces and managing general workshop repairs. You will find this 50-50 alloy most frequently deployed in heavy sheet metal fabrication, where extended working times and broad application surfaces are the priority. Adjusting the matrix to 63% tin and 37% lead hits what engineers call the eutectic point. At this exact ratio, the metal transitions directly from solid to liquid without a pasty phase, providing optimal flow for delicate electrical work. Conversely, shifting the balance to 40% tin and 60% lead creates an alloy engineered specifically to bond with galvanized iron sheets. When standard tin-lead mixtures fall short, metallurgists introduce external elements. Adding antimony to the matrix increases the final melting point to yield a mechanically stronger joint, while introducing bismuth dramatically lowers the required heat. Lead is highly toxic. Any non-fusion joint applied to domestic water lines, food storage, or culinary utensils requires a strict 100% pure tin alloy. Solder is an engineered matrix. The precise ratio of constituent metals is calculated to match strict thermodynamic demands of the parent metals it binds. Heat accelerates chemical reactions, making rapid oxidation the primary enemy of any non-fusion joint. Looking at this cross-section, the consequence is clear. As the base metal heats up, an invisible barrier of oxygen molecules forms across the surface. The molten filler metal simply beads up and fails to penetrate the joint. A chemical mediator is required to break the stalemate. We apply a substance called flux, which actively dissolves the oxidation barrier and strips away impurities. By drastically reducing the surface tension of the liquid metal, the flux initiates capillary action. This physical force pulls the molten alloy deep into microscopic spaces, filling gaps as narrow as 0.05 millimeters. Industrial fluxes are divided into two rigid categories based on their chemical aggression: corrosive and non-corrosive. Corrosive fluxes rely on heavy acids or alkalis. They clean metals with extreme efficiency, but leave a volatile residue. If this residue is not scrubbed away immediately, it will slowly eat through the parent metal. These corrosive agents are paired with specific base metals. Zinc chloride is used for copper, hydrochloric acid for galvanized zinc, and ammonium chloride for iron. Non-corrosive fluxes eliminate the acid entirely. Because they leave no damaging residue, they are mandatory for delicate printed circuit boards and dense electronics where post-solder scrubbing is physically impossible. These safe alternatives range from animal fat, known as tallow, to chemical pastes made of zinc chloride, resin, and glycerin. Pure resin, or biroja, is particularly effective as a powder that thermally activates only when the iron hits 80 to 100 degrees Celsius. Without this invisible chemical mediation, oxidation wins. The physical mechanics of capillary action are neutralized, and the joint inevitably fails. To melt the alloy and activate the flux, we rely on the final variable, the thermal delivery tool, or soldering iron. The functional tip of the tool, known as the bit, is forged entirely from copper. Copper's superior thermal and electrical conductivity allows the tool to transfer high temperatures into the work surface rapidly and consistently. The geometry of the copper bit dictates its application. A heavy, blunt hatchet shape retains the heat necessary for long seams on flat sheets, while a fine, pointed bit is required to reach into deep grooves and narrow channels. Before the adoption of modern 50 to 100-watt electrical heating elements, technicians generated this concentrated heat mechanically, relying on pressurized, liquid-fueled blow lamps. With the tool selected, technicians execute a strict 4-step industrial workflow. Step 1 is straightforward, bringing the copper bit up to the specific target temperature for the chosen alloy. Step 2 is tinning. Before touching the parent metal, the copper bit itself must be coated with flux and a thin layer of solder. Step 3 is tacking. Small, isolated spot welds are applied along the seam to lock the physical geometry of the plates firmly in place. Step 4 is floating. The technician pulls molten solder down the entire length of the seam, allowing capillary action to finalize the continuous structural bond. This 4-step physical workflow is the practical execution of the strict thermodynamic and chemical rules established by the flux and the alloy matrix. How do engineers apply these exact same principles when joining incredibly hard, dissimilar metals, or when an assembly requires massive shear strength? They cross the 450-degree thermal threshold, leaving soldering behind and upgrading the process to brazing. Brazing scales up the filler metal. The soft tin lead matrix is abandoned in favor of rugged copper and zinc alloys known as spelter, or silver solder, a highly durable blend of copper, zinc, and silver. The chemical mediator must scale up alongside the heat. Low-temperature resins instantly burn away under a brazing torch. Instead, engineers rely on borax, or sodium borate, a heavy-duty flux chemically engineered to survive 600-degree thermal loads while preventing rapid oxidation. This high-heat synergy allows manufacturers to permanently bond brittle, high-hardness materials directly to standard steel bodies without melting either component. You see this application clearly in precision measuring tools. The ultra-hard tungsten carbide contact tip of this micrometer is permanently joined to a flexible carbon steel or vanadium frame through brazing. Whether operating at 200 degrees on a fragile radio circuit board or at 600 degrees on a heavy industrial cutting tool, the core physics of the non-fusion joint remain absolute. Structural success is never an accident of applied heat. It is the deliberate, calculated synergy of metallurgical ratios, chemical catalysts, and precise thermal delivery.